Today we're going to try to understand a little bit more about binary mechanics by looking at its equations. The only mathematics that you need, a 3 or 4 year old child already knows because these three math ideas are built into language, understanding and speaking language. The first of these three ideas is the one-digit binary number, 0 or 1, yes or no, full or empty. The truth table for AND logic is shown below. Is it true that Jack and Jill went up the hill? If the little boy who went up the hill is 1 and the little girl who went up the hill is 1, then the statement is true. The output is 1, that both Jack and Jill went up the hill. Any other combination is not true. The third idea is not logic. If we have a 0, we make it a 1. If we have a 1 input, we make it a 0 out. So you don't need math based on continuous space-time theory using real numbers for every point in space and time, popular in the failed standard model formulations, which at best can only approximate physical events and which look like this. Yuck! Could you tell the roosters to stop making all that noise? What are you doing? No, don't use a shotgun. Forget it. In binary mechanics, we have structured space. We start with the idea of the spot unit, where we have two kinds of energy, M and L, shown by circles and arrows in our diagrams, and energy is quantized because M can equal 0 or 1, and the L can equal 0 or 1. These M and L types of energy occur in quantized space, a cube of size L, which is the primary constant in binary mechanics, to define the spot unit. 3 spot units make a spot in the X direction, the Y direction, and the Z direction. If we fool around and change the direction of the arrows, like shown in the lower left here, change the sign of the 1 states, which we call the M bits, and things like that, we get finally a spot cube, and our model of space is that it is a lattice of these spot cubes. For any theory of everything in physics, you only need 2 things. The system state definition, that's what do we have, and secondly, its time development, how it changes as time marches on. So now let's do like a walkthrough of the basic equations of binary mechanics. We have our 2 energy types in equation 1, which is actually 2 equations which we saw on the last slide. M equals 0 or 1, and L equals 0 or 1. Now that was the spot unit. We combine 3 of those to make a spot. So if we collect the states 1 or 0 of the 3 M loci and the 3 L loci, we have what's called the bit function, which replaces the antiquated, outdated 20th century quantum mechanics wave function. Now the bit function can include any number of spots. It just depends upon how big your computer is, how much computing power you have. What we need to do is take those computers at the US National Labs and CERN over there in Europe and use those computers, say, to model the cesium-133 atom, which is a clock, and see frame by frame exactly how it works. That's the new technology that binary mechanics brings. Next, we're going to define the binary mechanics space, S sub I, in 3 spatial dimensions as a spatial frame, and yes, it has integer coordinates. We define then the parity of any position in this space by this formula, and that parity is going to equal 0 or 1, even or odd. And so for each dimension, S1, S2, and S3, so X, Y, and Z are even or odd. Next, let's consider the X, Y, and Z dimensions in our space S as a cyclic ordered set, or what we call chirality, we're going to let the I, J, and K represent the three parities of each spot unit oriented along a particular dimension. And we have a set of equations here which describe this chirality and maps X, Y, and Z to I, J, and K. Using this information, we can then define the charge for an M loci, both its electric charge and its color charge, and the direction of the L loci. Does it point to the right or to the left? So we take a function that we're going to call sine of the M loci, and we're going to raise -1 to the power of the I parity. And that's going to equal +1 or -1 for, say, electric charge. And we know from simple algebra that if we raise any number to the 0 power, it equals 1. Or if we raise -1 to the power of 1, it's -1. We can get with this sine function a property of M loci, depending upon their position in any spot unit, of +1 or -1. Likewise, we can do the same for the L loci in equation 6 here, by raising -1 again, but this time to the power of the K parity, which gives you the direction, +1 or -1. And we just establish a convention that +1 is going to be right or left, and -1 is going to be the other direction. And we go along our jolly way, and we've now defined our system state. Now, that wasn't too tough, was it? That was pretty good, I think. And that's 1/2 of everything you need for a theory of everything. Just by defining the system state, we get a whole lot of results. Let's look at this table. Here's our bit function for the X, Y, and Z dimensions of our space. There are the 8 types of spots, which are the modulo 2 parities of each of these spot units. Each of these spots corresponds to an elementary particle, shown down here in the lower left. We can represent the M and L bits here with symbols where we have the arrow pointing to the left or to the right for minus and plus L from our sine functions, and the same way with the M bit being plus or minus with the plus and minus symbols to symbolically represent the spot units. And the different permutations of them actually predict 8 elementary particles, which is less than the ridiculous number of elementary particles that you see in many publications about the standard model of particle physics. Actually, all those other particles are combinations of these fundamental 8 particles here. Now we can show the same thing with signed pairs, where M or L equals 0 or 1, and these 0 or 1 states can be shown to have a unique configuration in the 3 spot units in each spot or each elementary particle. For example, when the M is -1, we have a lepton known as the electron. If all 3 M's are positive, we have the right-handed electron known as the positron in the lepton category. Here for reference is the signed complex version of what we showed above, just for you guys that love complex numbers. So what are the properties that we can derive or discover from the simple system state model that we presented? A whole boatload of stuff. For example, the charge Q is the sum of our sine M sub I values divided by 3. So if we have 3 minuses, that's -3, divide by 3, and we get the charge of the electron as -1. Next, we can get the handedness, right or left, by multiplying the 3 L sub I quantities together And that equals h, the handedness, which is right or left for that particular elementary particle. And we see here that if all three L's are minus, we're going to have minus 1 times minus 1 times minus 1 equals minus 1. That might be on the test, so you might want to write that down in your notes. The same way with the positron, we have the 3 plus L's. Multiply them together, 1 times 1 times 1 equals what? We're waiting. It equals 1. It took a long time to compute that, right? So our handedness for the positron is plus 1. Now, for these three d or down quarks, they're all right-handed, plus 1, as shown down below. And we have the three colors, red, green, and blue. And by the way, those colors also depend upon the M locus sign function, and we'll leave that for another day. But the three colors are predicted. The same way for the three antimatter quarks, blue, green, and red, which are left-handed. In the appendix of my paper, Binary Mechanics Postulates, we also show the equations to derive four colors. A lot of particle physicists talk about three colors, but there's four. The four colors, red, green, and blue, are shown correctly here for both the antimatter and the matter particles. And the fourth color is no color, 0, for the leptons, the electron, and on the left here, the positron. So our four colors are also predicted simply by the location and orientation in the X, Y, or Z directions of our spot units. This is a remarkable set of results from such a simple 6 equations of the system state of binary mechanics. By the way, I say 6 equations, but you could say there's more because equation 1 is really 2 equations, and there was all the chirality mapping that we did down there. And so the point is that all of the information is there. So however you want to list it, it's very important that all the information is there, because in order to write a computer program to do all of this, you have to have exact information inputs. It can't be, well, it could be this, or it could be that, or maybe it's the cat's dead, or the cat's alive in the box, or the Schrodinger cat, and all of this nonsense. You have to know exactly what's going on in order to even write a computer program to do that, to do the simulations in the free download of the Binary Mechanics Lab software. So if you like to tinker around, get that software, okay? Now let's look at the rest of the story. I said all we needed was the system state. We did it. Now let's do the time development, which is the bit function change over time.